need the answer. Good morning. I need the answer to this problem. At the same time, it's my attendance. Because you will notice that it will require your name. Yes. Let me do that. That's a nice multiple choice question. So which set of reagent would be best? Between what? B and C? Yeah, there's a big difference between B and C. That's a good question. In B and C, when you run the reaction in the lab, for B, you have bromine, you mix the bromine with water before you mix it with the reagent at once. Okay? Whereas with C, you first react it with bromine, and then you now add water. So that makes a whole lot of difference. So whenever you see the number 1 and 2, it means that they are adding them after the other. So they will add one, they will react before they will add the second one. But when we don't put numbers like in C and A, it means that we put them all together at once. So E, E means we first add Br3, BH3, let it go, let the reaction run, and then we add this, let the reaction run, then we add this, and let the reaction run. Does that make sense? That's the difference. And that will bring a whole lot of difference in the reaction. That will make a whole lot of difference in the reaction. So, what's the answer? A lot of people are going with C. Everybody must participate, okay? Because that's my attendance. Don't forget. Correct answer is B. Okay? Correct answer is B. Let me see. Yeah, a lot of you went with C, but the correct answer is B, okay? So in order to form hydrobromination, this is called hydrobromination. This is a hydrobromination reaction, okay? Sometimes I like to call reaction by their names because it reminds me of what the product will be. Does that make sense? So when I call this a hydrobromination, that's simply because the hydro reminds me of the OH, okay, coming from water. And then the bromination is the bromine. So this is an example of a hydrobromination. So in a hydrobromination reaction, everything is added together. They're all added at once. Yes?
So you said the difference between B and C is that B will react them together and then C...
B would just put everything together at once. So you have your bromine, your water, and your alkene. You all mix them at once. Whereas with C, you have your alkene and the bromine. You let them react first. When they are done reacting, then you add water. And if you do that, if you do C you will end up with dibromination, vicinal bromination. If you do A instead of having the OH, you will have OCH3. Does that make sense? If you decide to perform A with A, that's exactly what you will have. Does that make sense? Those who came late, you have another chance to take attendance. Second chance to take attendance. And I want everyone to participate. So Malik, scan. I haven't seen you scan. Scan it, Malik. Okay. Okay.
Oh, this is how we take attendance?
Of course. That's a new strategy. Attendance plus participation, everything at once. It goes in. Everything at once. And then participation will be the number of times you do the job, you know. If you only scan once, you only participated once. If you scan 2, 3 times, then you participated 2, 3 times. Does that make sense? Yes. Attendance / participation. If you scan once, you only participated once. It's better to participate and even choose the wrong answer than just sit and not participate at all. Okay? I want a participation. I want a participation.
So you're going to start every class
Like that.
Can we do like a 5-minute grace period because you have 8 o'clock?
Well, right now it's 10 minutes past 8, so you are 10-minute grace period. I haven't started my class yet. So now we have a 10-minute grace period. And we are not done. We still have number 3 to answer. So that would technically be a 15-minute grace period. And for those who go and scan my video, after I post the video, they don't come to class, then they go later on and scan the video. It doesn't count. Unfortunately, Google Form gives you the exact time you scan. So when you scan after posting the video, I know. Okay, so I will not consider you. Yeah. Because, yeah, some of you did that for the last one. You went and then looked at the video and then scanned the video. Well, I upload. No, I know those who watch the video know what I'm talking about. Those who don't watch, that's fine. Huh? No, at least I knew they watched the video, but they didn't watch the video because they would tell you how long they stared at my video, right? YouTube tells you everything. How long did he stare at the video? If you look at my video, 1 hour, 2 minute video, you watch it for 30 seconds. What will you understand? Statistics. It keeps everything. So don't fool yourself, guys. Don't fool yourself. Like it. So, what do we all go with? Let me see. What do we all agree? Let me check my participation. It's important. Oh, 41 in this other one. No, not that one. Let me check the other one. There's a big problem. There's fire on the mountain. A lot of you guys chose A. A lot of you guys choose A. You all want to choose A because you didn't apply your Markovnikov rule. You didn't apply the Markovnikov rule. That's why a lot of you want to choose A. So, what is the correct answer if you apply your Markovnikov rule? Correct answer would be D. A lot of you want to choose A. A will produce a Markovnikov product. According to Markovnikov, you know, these are the 2 carbons of interest. Those 2. Now, this carbon here is connected to 2 hydrogen. This other carbon is connected to 0 hydrogen. So according to Markovnikov, which is A, the one with 2 hydrogen will have more hydrogen. And so the product for the Markovnikov reaction will be that one. So this is an anti-Markovnikov product. And for hydration, to form an alcohol using anti-Markovnikov, you need to do hydroboration. You have to do a hydroboration. Does that make sense? So D is the reagent required for hydroboration. And take note the way the reagents are. You first add borane and let the reaction go. Then you now add the hydroxide in the presence of a peroxide. Does that make sense? So don't forget that. Yes. How do I know that is a hydroboration? Say that again. I can't get you very well. Well, we'll have a summary. We'll have a summary because in this case, that's what I would say you need to memorize it. Or if you read, you'll be able to find it. Because you need to be able to classify your reaction. What kind of reaction will lead to the formation of an alcohol? You need to know them. What kind of this. So that's the only way you can know it. That's the only way you can know it. I cannot know it by just looking at the reagent. Okay? You just get used to it. You just get used to the reagent. Yes. THF is a solvent. Tetrahydrofuran. It's just a solvent. Okay? So at the end of the day, you need to know that when I see this reagent, it means I'm forming this kind of stuff. Or you need to be able to also know that if I want to form this, I will need to have this type of reagent. Does that make sense? And the best way for me to know the reagent is to know their names. That's what I do with you guys. If I want to be close to you, I need to know your name. I need to be able to call you by your name. You feel more familiar with somebody that will call you Destiny Ball than somebody that will say, hey, that girl. Does that make sense? If I just call her, hey, that girl, it will not feel, I will just forget her the next minute. But if I do the effort to study her name, Destiny, then I will know her. Does that make sense? So when I call this reaction hydroboration, just the fact that that hydro is there, it will keep reminding you that the product will have an OH. And the boration comes from borane, which is this BH3. It means I'm using borane to form an OH. That's why it's important to also know the name of those reactions. The first one I told you was what? Hydrobromination. It means I have a hydro and I have a bromine. The hydro is the water part. The other one is a vicinal or dibromination. It means I'm using two bromine to add dibromination. So knowing the names also is important. That helps you, keeps you on track. That makes sense? Now the grace period, third grace period. That's the third grace period. Remember, if you participate once, participation is once. If you participate twice, participation is, right, Diana? So it's official. Your exam number 2 will be on Thursday, February 27th at 6:30 p.m. It's official. Your next exam will be on February, Thursday, because you guys don't even come to class on time. No, you guys don't even, you just ask me a grace period. It doesn't work. So Thursday, February 27 at 6:30, we're meeting in here for your exam number 2. Then you guys can go to Florida, Miami Beach, and then have fun for the spring break. Okay? Then you can, and then avoid having coronavirus. Yes. Chapter 5, 6, 9. Chapter 5 is just the nomenclature and stability of alkane, then 6, 9. Okay. So which of the following molecule is a possible starting material for the ozonolysis reaction? Let me see what you guys think. Oh, Steve? You still scanning it? Like, yeah. Let's see what you guys think about it. You did it? Only have 26 people in class or what? Or 29? Ah, you guys said. But I thought you guys have done that already. Wow, that's like a 20-minute grace period. Wow. That's a lot of time. So are we good? Let me see now what is in your mind. I still have very few participation. Like, many people are absent. I have some people that are absent. Oh, very, very, very few people had the correct answer. Very few people had the correct answer, guys. Very few, very few. Who are those who said E? Who said E? Who are those who said E?
I didn't even see E down there. You can see it, but you didn't notice it.
You cannot see E. E says molecule A, C, and D. Correct answer is E. The correct answer is E. Okay. Remember ozonolysis, all you have to do is split the double bond into two. Okay? So if I take molecule A, if I split this into two and I split this into two and I cap both ends, I will form that product. Do you see that? No, how? Look. If you divide that into two, look at this upper end here. That's the product. That upper end is the product and that lower end is also the product. Because you split them and then cap them with oxygen. Well, it didn't tell you that it's a balance equation. What did it say balance equation? So, is that okay with the first one? First choice. A. Okay. Now, let's look at choice C. Same thing with C. If I split that into two and then cap it with the oxygens, it will give you that product. And the same thing with D. D, I will divide this and divide that, and then cap each of them. So B, it will not work because B will give you aldehydes. Look at B very well. B, this is a ketone. This is a diketone. With B, if you do that with B, remember you have hydrogens here. So if you split B, you will instead have something like this with the B. If you do with B, this is what you will have with the hydrogen there. That's what B will give you. That's why B is wrong. Does that make sense? So B will give you the aldehyde instead of the ketone. So the correct answer is E. Molecule A, C, and D. So that said, from your textbook, I have selected a series of problems for you guys to try. Problem number 64, problem number 66, problem number 69, problem number 74, problem number 75, 94, 96, 101, 103. Those are good exercises from your textbook. I didn't say you should limit yourself to those one. I didn't say you should limit yourself to those. Those are simply good exercises that you can practice and try to master this reaction. Yes?
Is there an easier way for us to see, like, when you split it, what it would form? Because just looking at that, I don't really see that. I just,
Yeah. Let's look at C, for example. Okay? I'll take C because it's the easiest that I can easily draw. That's a C. So if I split this, basically what I'm saying is, after splitting that, I will have, that will be the double bond. Like I'm breaking the double bond. Okay? So when I break that on each end, I now add an oxygen. On each end of that. That's the same thing you do with everyone. So once you break, on each end you add the oxygen. And so you notice that's exactly the same molecule as this one. Just that it's folded. Then the same, it's exact same molecule, just that one is folded and one is extended. So if you do the same with the rest, you will end up having the same thing. It gives you the same product. Let's continue with the class. So this would be a summary for those who are asking me how to know your stuff. This is the last slide. This is the last slide. The last slide. It is a summary, but I don't really love it because it doesn't tell you much about the stereochemistry and the stuff. I will post another summary that will give you everything. So we've seen basically all these reactions. Hydration, hydroboration. This is another form of hydration because this is with the alcohol and that is with water. So if you know this reaction, then you should know this one because they're exact same. One uses water, the other one uses the alcohol. We've seen this. This is ozonolysis, where you simply split the double bond. This is in reaction with the epoxide. So that's epoxidation. We did that here and we use NCPDA. This is hydrogenation. That's exactly what you guys did in the lab. Last time in the lab. Adding hydrogen. And then this is hydrobromination. We talked about it again this morning. This is dibromination or vicinal bromination, where you're adding a bromine to both carbon. And I'm meeting you guys to see the difference, okay? Here is bromine and water, here is only bromine, or bromine and methylene chloride, sorry. Then that is bromination, hydrogen. That's a bromination and this is a dibromination. So this is monobromination and that's dibromination. Or this dibromination, sometimes we refer to that as vicinal bromination. That's just it. Okay? And so if you're able to know these, then everything we have to do now is just changing the type of alkenes we have. And then you now have to keep in mind, okay, when can I have a hydra shift? When can I have a methyl shift? All those things you have to play with them. Does that make sense? When can I have a hydra? When can I have a methyl? Which one follows the mechanical rule? Which one does not follow the mechanical rule? Those are the things that you need to know. And so at the end here, you can easily put follows mechanical, does not follow mechanical, follows mechanical. This one is not interested in mechanical, not interested, follows mechanical, it doesn't matter. Follows mechanical. And you say it doesn't matter because you're adding two bromines. Does that make sense? And so if you can populate it. So what I mean to say is this. What I mean to say is this: a Markovnikov, anti-Markovnikov, Markovnikov, doesn't care, Markovnikov, and doesn't care. That's it, you know, and that's how you will know it. That's how you will know it. And so in addition to this, today we have now to add an extra component, which is the last component, the stereochemistry component of the reaction. That's the last component we have to add, the stereochemistry, okay? So let's go back and then start looking at what the stereochemistry of the reaction is. So at the beginning, I think we said reactions are radioselective. This reaction is radioselective. So when we talk of radioselectivity, it means that the reaction has a possibility of forming two constitutional isomers. It has a possibility of forming two constitutional isomers, and one of the constitutional isomer is preferentially formed over the other. That's why we say the reaction is radioselective. Does that make sense? When you have the possibility of forming two constitutional isomers, for example, if I give you this reaction, if we have that reaction and we decide to do a bromination, there are two possible products. The first product, and then the second product, okay, do you see that? If we do the hydrobromination, those are the two possible products, the red and the blue. And the red and blue product are example of constitutional isomer because the connectivity is different. The way the bromine is connected is different. But one of them is preferentially produced over the other. Does that make sense? And in this case, which one is preferentially produced? Does that make sense with everyone? The red one is preferentially produced. Is that okay? And so this reaction will describe this type of reaction as being radioselective. So if I ask you what is the major product of this reaction, the answer will be the red one. If I ask you what are all the possible products of this reaction, in that case, both of them are the possible product of the reactions. Does that make sense? And when I do it, I want you guys to be dreaming about the mechanism in your head. Yes. That's why I was saying you should dream about the mechanism in your head. Can someone help us with the answer? Why is the red one? Because it will produce a more stable intermediate, which is what? What is that stable intermediate, guys? That means you are dreaming about the mechanism in your head. It's a tertiary carbocation. Does that make sense? So, in addition to that, the red one follows Markovnikov rule. Does that make sense? In addition, okay? So, if I have that, that's my mechanism. You attack here, and then you go over there. There are two things I can form. The two carbons here. One gets the positive charge, the other one has the hydrogen. That's the intermediate. So, my intermediate here, I will have a positive charge here, and then here I will have the hydrogen. Or, I will have this other case. The positive charge here, and then the hydrogen. Those are the two possible intermediates. And in this case, the blue intermediate is more stable because it's a tertiary carbocation. Does that make sense? Yes, Amalia, you had a question. Thank you. Now, a reaction can also be stereoselective. Remember what the stereoisomers are. Stereoisomers means they only differ in their orientation in space. The R and S. Those are the stereoisomers. Okay? R and S. So, there are some reactions that will preferentially form the R isomer over the S isomer. Or there are some reactions that will form the same amount of R as the same amount of S. In that case, you will have what we call the racemic mixture. You remember what the racemic is from 301? That a reaction with equal amount of R and S. So some of them will generate the racemic, some of them will preferentially generate the R, some of them will preferentially generate the S. Does that make sense? And so we'll have to learn them, which one will do what. Does that make sense? And then, in addition to stereoselective, there's a stereospecific. That to produce a specific stereoisomer, you need to start with a specific stereoisomer. Means that A can only produce B, and C can only produce D. Although A and B are stereoisomer, let me explain this. Let me explain that in detail. If I have a double bond, I will have the trans of the double bond, and I can also have the cis counterpart. The trans can only produce a specific type of stereoisomer, which the cis cannot. Does that make sense? Those are the reactions we refer to as stereospecific. The trans can only give you a specific type of product, maybe the R product. And then the cis can only give you a specific type of product, maybe the S product. Those are called stereospecific. So take the note of the difference between the stereospecific and the stereoselective. Yes.
You're saying stereoselective A can make B or C?
It can make either one. Yes. So, when you do a bromination reaction, it's always good to look at your product. For example, if I react this propene molecule with HBr, that would be my product. And if you look at that product, there is no chiral carbon. Okay? There is no chiral carbon in there. And because there's no chiral carbon, then I will not have any stereoisomer. In order to have a stereoisomer, I need to have a chiral carbon. So it's always important to look at the stereochemistry of the product. Look at the product and then decide if there's a chiral carbon or not. Now, sometimes your product can be a racemic mixture. You remember what we said? A racemic mixture is an equal mixture of the R and S enantiomer. When you have equal amount of R and S enantiomer. And it turns out that bromination reaction will always lead to the formation of a racemic mixture. All bromination reaction. That's how you know it. It will always form a racemic. And you need to understand why. If you do the reaction mechanism of this, what would be the intermediate? A carbocation, right? You guys don't want to answer me, right? Don't answer. Yes. If you guys don't want to answer, I will answer myself. That's the intermediate for the reaction, right? If you want to do the mechanism of this reaction, that would be the intermediate, your carbocation. Question: what is the hybridization of that carbocation? What is the hybridization of this carbon? Say that again. What is the hybridization? SP. Okay, the hybridization is an sp2. How do I know that? Because we have 3 bonds, right? We have 3 bonds surrounding that carbon. There are 3 bonds. 1, 2, 3. 3 sigma bond. That's the meaning of sp2. S1p2. 1 plus 2 gives you 3. Does that make sense? That's the way I remember it without memorizing it. S1p2. So that gives me 3. So I have 3 bonds. So that's an sp2. Chem 201. What is the geometry of an sp2? If you have a hybridization sp2, what is the geometry? Someone is saying it here. Who is saying it? Yeah, trigonal planar. Okay? sp2 molecules are flat, trigonal planar. So because they are flat, like this piece of paper, it means that a nucleophile can attack it from above and from below equally. Does that make sense? Because the molecule is flat, it means that the incoming nucleophile has an equal opportunity of attacking the carbon or of attacking the carbocation from above or from below. And so if it attacks the carbocation from above, it will produce one of the isomer, maybe the R. And then if it attacks from below, it will produce the other one. I don't know, maybe the S. Does that make sense? And so because in terms of probability, it has equal chances of attacking, that's why you end up having a racemic mixture. Does that make sense? So if you want to see that in picture form, this is what it will tell you in a picture form. So in picture form, you have your carbocation over there, which is a flat molecule with the p orbitals hanging around. And so your nucleophile, which is bromine, has an equal chance of attacking from above or attacking from below. And when it does that, you end up forming your product. Does that make sense? And you form them in equal proportion, the R and the S. And so that gives you a race mate. That gives you a race mate. Yes, ma'am.
Wouldn't it only be true if it's just like a regular alkene or like nothing else attached to it?
Say that again.
Would this only be true for like regular alkene that doesn't have anything else attached to it?
Yeah.
Like other electronegative things, or is still the same?
Well, in general, hydrobromination will always give you a race mate mixture. In general,
Okay.
yes. So in this case, this reaction is stereo selective. Okay, this is a stereo, it gives you a mixture of those things. And so whatever, if you use the Z or the E, whatever one you use, they end up giving you the same kind of intermediate. Remember, we are trying to see if the reaction is stereo specific. We are trying to look at it, if the reaction is stereo specific. Normally, for this reaction to be stereo specific, if you start with the Z, that should give you a specific type of product, which is different from the product that the E will give you. But in this case, both Z and E gives you exactly the same type of product, a racemic mixture. So this reaction will not be stereo specific. Okay, it is a stereo selective reaction. It produces a racemate. Does that make sense? That's why it's important to know the mechanism. And so you guys can conclude now. You can actually make a clear conclusion that all reaction that goes through a carbocation intermediate will always give me a racemate. Does that make sense? Because that carbocation intermediate is flat, and so you can attack from above or from below equally, and so you end up having a racemate. That would be a genuine conclusion. You will not be wrong saying that. Everything that goes through a carbocation intermediate will do that. Yes. It will only do that if your intermediate is flat. If the intermediate is not flat, then there will be preference for one over the other. Does that make sense? Yes. Selective. Yeah, not quite, because we'll get to the next example. Here, if you already start with a molecule, take note, you start with a molecule that already has a chiral center, and then you cause the reaction to take place, you will produce another chiral center. In that case, you are producing diastereomers. Remember the meaning of diastereomer. Di means two. Diastereomer, it means you have two chiral centers in the molecule. Like here in the product, you see you have two chiral centers. Think about it. You started already with the chiral center. The chiral center was already there. And now you conduct your reaction. That goes through an intermediate. This is an intermediate here. It's a carbocation, so it is flat. It has the possibility of giving you the R and the S. That's why you will have those. And so in addition to these new centers that you created, there is the old center. And so each of them will now have two centers. That's why we will form a pair of diastereomers. Does that make sense? Yes. Those are all stereo-specific reactions. Those are all stereo-specific reactions. Does that make sense? So in order for you to have a diastereomer, you need to start with at least one chiral center, and then you produce another chiral center. That's how you will end up having a diastereomer. There's also the possibility of forming a diastereomer if at the end of your reaction, if you start with 0 chiral center but ends up with 2 chiral center. So whenever you end up with 2 chiral center, chances are that you will form a diastereomer. And so whenever you have your product, always look at it very well and ask yourself, do I have 2 chiral center? Okay, so it's possible. So for example, here we're starting with a molecule with 0 chiral center, and then over here we end up having 2 chiral center. So you will have a mixture here. The 2 chiral centers could be SS, they could be RR, they could be SR, or they could be RS. Does that make sense? So you will have that bunch of mixture in there because you've created 2 chiral center. So it will generate that bunch of mixture. Does that make sense? We're only learning the stereochemistry. And so for this specific example, you remember I said you will have a bunch of mixture in there. And these are the mixture here. So the next slide is only an explanation of the different probabilities of those mixtures. It's the different probabilities. And so your final product will be this. This will be your final product over there, which is that bunch of mixture. Some of them are SS, some of them are RR, some of them are SR, some of them are RS. It's your duty to go and find out which one is SS, which one is RR, and which one is what. Does that make sense? It's your duty to go and find out which one is SS, which one is RR, and which one is what. That's your duty. Well, the intermediates. Yes, because, oh, say that again. Yes, it's a carbocation. Yeah. So does that make sense, guys? Okay. I will talk more about syn and anti-addition in a couple of slides. Now let's look at the hydrogenation reaction that we did together in the lab last time. When you perform a hydrogenation reaction, it turns out that the hydrogen that you are adding adds up on the same side of the plane. When you have a plane, remember the double bond is flat. When you have a plane, you can add both hydrogen above the plane, or you can add both hydrogen below the plane. The most important stuff is that the hydrogen adds on the same side of the plane. So either or above or below. And in that case, when they add on the same side of the plane, we refer to those type of reaction as a syn addition, meaning on the same side. So hydrogenation is an example of a syn addition as opposed to an anti-addition, meaning adding on opposite side. Does that make sense? Hydrogenation is an example of a syn addition. Now, hydrogenation, being a syn addition, is also a stereoselective reaction. Okay? A hydrogenation is a syn and it's also stereoselective. You remember what we said about stereoselective. Stereoselective means that a specific stereoisomer will produce a specific stereo product. That's the meaning of specific. Does that make sense? So hydrogenation is also stereospecific. What I mean by that is, if your starting material over here, what is it? Is that an E or a Z? This is a Z, right? That molecule here is a Z. It's the same size. Huh? Yeah, so that's a Z. So if you start with a Z, then you will form what we call an erythro enantiomer. Oops. If you start with a Z and perform a hydrogenation reaction, you will start with an erythro enantiomer over here. You will start with the erythro enantiomer, and I want you guys to look at the stereochemistry for the erythro enantiomer. Both hydrogen are on the same side of the plane, and that's because we started with the Z. And you can look at that from the Fischer projection. In the Fischer projection with the erythro enantiomer, the hydrogen you added are on the same side over there. That's my erythro enantiomer. So it is a syn addition, and I would say what? Stereo specific. Scene addition and stereo specific. You remember what a meso compound is, guys? Yeah. When the centers are exactly the opposite of the other one. If one center is R, the other one is S, and then the substituent around the centers are exactly the same, then that's a meso. Does that make sense? The centers are opposite to each other. That's the first condition. The second condition, the substituents around the centers are the exact opposite of the other. Then that gives you a meso. And meso are optically active or inactive. Which one? I don't know. Remember, remind me. They are inactive. Perfect. Yes.
I get how you get that product, but how do you know it's the two B's that are on the wedge or the...
You can put them, both of them on the wedge or both of them on the dash. But they must be on the same type of bond because it is a scene addition. Does that make sense? The question was, how do I know that the D or the hydrogen will be on the wedge? Just make sure that the same group are on the same type of bond because we are looking at a scene addition. Does that make sense? The same group are on the same type of bond. Perfect? Gracias. So this is a meso because we'll have two chiral center, and you can notice that the two chiral centers have exactly the same type of substituent. And so your product will be meso in this case. Yes?
So this reaction will have two products. You'll have another product where it's the opposite.
It will be the same product.
Both will be in different directions or
Look, for example, I haven't determined the stereo centers here, okay, the stereochemistry. You can do that. This might be the S and this might be the R. The other product will be the R and S. And because they are meso, they're exactly the same people.
oh, okay.
Yes.
This is only hydrogenation.
This we're only looking at it at hydrogenation. Okay? We're only looking at it in the hydrogenation. And that can also be true if you do the bromination, dibromination, because you're adding two bromines. Does that make sense? It can be true when you're doing because you're adding two molecules of the same type. But in hydrobromination, it will not work because you're adding one bromine and one OH. And so the chiral center, even if you form two chiral centers, they will not have the same type of substituent. So meso can only occur if you're adding the same type of group to both carbons that already have the same type of group substituted. Now, if you do a scene addition to the trans, remember, we're still looking at hydrogenation. If you do a scene addition to the trans isomer, this is the E isomer. We're talking about the Z. If you do a scene addition, remember, scene addition means you're adding the hydrogen on the same side, okay? And so by doing my scene addition, the hydrogen will be on the same side of the plane. But it turns out that the product would be a trio. You remember with the Z, we form the erythrio, but with the E, we form the trio. And you can easily see that trio by looking at the Fischer projection. On the Fischer projection, one of the hydrogen will be on the left and the other one will be on the right. Does that make sense? That's the meaning of trio. Trio, one is on the left, the other one is on the right. Erythrio, they are all on the same side. Either all on the left or all on the right. Does that make sense? I don't know. That's probably Latin. That's probably Latin. I don't know. Who can speak Latin here? Then why are we teaching chemistry in Latin then? Nobody knows Latin again.
All the languages come from it.
Yeah. Yeah, that's too bad. So what I want you guys to remember here is the E isomer, if it performs a scene addition, it will lead to the formation of a trio product. Does that make sense? The E isomer performs a scene addition to give you a trio product. And then the Z isomer The Z isomer performs a syn addition to give you an erythro product. Does that make sense? And all of them are stereo specific. They're stereo specific because the Z gives you the erythro and then the E gives you the trio. That's why we refer to them as stereo specific. Oh God. In addition to a cis isomer, forms only the cis stereo isomer. Well, so it's the same thing we've been talking about. So we have a cis isomer over here, and so we expect our product over there to be an erythro because we're doing a syn addition. Okay, so these products are erythro. The hydrogen, if you draw the Newman projection, they'll be added on the same side, either above or below the double bond. I don't know why we had to repeat this slide. Same thing with the trans. I will skip this. That's just giving us different cycloalkane rings. It's not important for me. So we don't. This is all with hydrogenation. So what I want you guys to remember with hydrogenation is this. If you start with a Z isomer, hydrogenation can only be a syn addition, and your product will be erythro, meaning that if you draw the Newman projection, the hydrogen will be on the same side, either both of them on the left or both of them on the right. Okay? With hydrogenation, if your product is a trans product or an E product, you will perform a syn addition, and then the product will be trio. So trans trio, TT. Does that make sense? A T gives you a T because you're starting with a trans, you end up with a trio, TT. Is that okay for memorizing? That makes life easy. TT, that's what you need to remember. Is that okay? And then now you can only form a meso by observing your product. You look at your product and you say, okay, I have created two chiral centers. Are the two chiral centers exactly the same? Do they have exactly the same type of substituent? If the answer is yes, then you will tell me that this product is meso. If the answer is no, then this product is not meso. Does that make sense? So we've talked about forming a racemate, and we've talked about forming the trio and the erythro. Yes?
Is that only talking about we're doing the erythro measurement, or can it be in the trio? Can it be a meso compound?
Yes, you can also have a meso compound in the trio. You can have meso both erythro and trio, right? You can. The only thing is that when you get your final product, once you reach to your final product, you observe that final product and say, okay, I have created two chiral centers, whether trio or erythro. Are those chiral centers exactly the same in terms of the substituent around them? If the substituent around them are exactly the same, irrespective of the fact that it is a trio or an erythro, then you have a meso. Does that make sense? That's what I mean to say. Okay. Of course, one of the center must be the opposite of the other, right? One is R, the other one is S. We shouldn't forget that. When you do a peroxide addition, for example, R, this is a peroxide acid. When you do a peroxide addition, most of the time you will see this guy, MCPBA. Last year when we gave this exam, we gave the full structure of MCPBA to the student. All of them were off because they have never seen the true structure, whereas I gave them in class. I drew, instead of writing MCPBA, I drew out what that molecule is all about. And you have that molecule in one of these slides. So familiarize yourself if you see it. All you need to remember is if you see a molecule with this guy, that functional group there, look. With this functional group, oops, no, what's wrong? If you see something with this functional group, carbon double bond OOH, then you know that you are forming an ether. You know you are forming an ether. Does that make sense? And so the ether formation is a syn addition. the ether formation is a syn addition. So that means that the oxygen, these bonds, are all formed on the same side. That's the meaning of being a syn addition. That's all I need you guys to remember. That peroxy acid is an example of a syn addition. And so we'll have a couple of examples over here. You start with the cis or the Z, and then you do a peroxidation. At the end of the day, your product is a syn addition, meaning that the groups are on the same type of bond. So we have the hydrogens and we have the metals. The oxygens are connected on the same type of bond. That's the meaning of being a syn addition. Okay. Now, another thing we need to remember is that a syn addition to a cis product, the syn addition to the cis product will also give you a syn addition to a cis reactant gives you a cis product. For the peroxidation, cis gives you a cis. Okay, what I mean by cis is that the both groups are exactly on the same type of bond. The bulky group on the same type of bond. But if you do the syn addition to a trans over here, the product also will be a trans. The groups will be on opposite type of bonds. I want us to take note of that. To the trans product, it gives you a trans. To a cis, it gives you a cis. Does that make sense? And how do I know that? Because I'll be looking at where your bulky groups are. Are the bulky groups on the same type of bond? If yes, then you probably started with a cis product. If no, then you probably started with a trans product. Again, there's a possibility of having a meso compound, okay? There's a possibility of having a meso compound. And that's only true if your substituents are exactly the same. Because if I split that molecule, I will have a chiral center here and a chiral center here. And you notice that they have exact same type of substituent. So I can also form a meso. You can only form a meso if you look at the product. You draw the product, you observe the product, and then you make a decision if that gives me a meso or not. Let's look at the stereochemistry of hydroboration. You remember what hydroboration is? Hydro means you're adding an OH. Hydroboration follows the anti-Markovnikov reaction. And hydroboration gives you a syn addition, meaning that you are adding the OH and the H. Because in a hydroboration, these are the two groups that you are adding to the double bond. And so if it is a syn addition, it means the OH and the H are all added to the same side of the bond. So they will either be both wedge or dash. That's the meaning of being syn addition. Okay? They are both wedge or dash. And that's what we have here as our product. And again, this is another example of hydroboration. You will see that here, they are both on the dash, and over here they are both on the wedge. And again, I will emphasize, observe the molecule to see if you can have a meso compound. Okay? Observe the product and see if that gives you the meso compound. Vicinal bromination. Vicinal bromination is an example of an anti-addition. It means that you are adding the two bromines. Remember, vicinal bromination, you are adding two bromine. And that vicinal bromination is anti, meaning that one bromine adds above, the other bromine adds below. And that you can understand it if you have a look at the mechanism. If we do a critical look at the mechanism, it goes through the formation of a bromonium ion. The bromonium ion is a kind of triangle. Okay? And so when you have that triangle, the first bromine already occupies the top position. And so the second bromine can only attack from below because the top position is already occupied. Does that make sense? And so the second can only come from below, and that's why they all end up being added on opposite side. One will be added on the top, the other one will be added on the bottom. One on the top, the other one on the bottom. That's what we call the anti-addition. Does that make sense? One is above, one is below. In other words, one will be on the wedge and then the other one will be on the dash. Does that make sense? It is an anti-addition. So for anti-addition of a cis isomer will only form the trio. You remember what trio is? It's good to look at them from the Newman projection, from the Fisher projection. The trio means that they will be added one on the left, one on the right. That's basically what anti means. Okay? So you only form a trio with a cis addition. One will be on the left, one will be on the right, on the opposite end. If you do that kind of addition, anti-addition. That's the opposite of a cis, of a syn addition. With a syn addition, the cis gives you the cis, the trans gives you the trans, or the trio. Does that make sense? And so the trans product, in this case, will give you an erythrio. The trans will give you the erythrio. Oh, life. A lot of stuff to do. For anti-addition, if your reagent is a trans, then the product will be erythrio for anti-addition. But for a syn addition, if your reagent is a trans, your product will be trans. Does that make sense? Okay, I think I will save you guys. I will save you guys. So we have a clear, this is a summary of all what we've been singing this morning. We have a summary of that, all what we'll be singing. Okay. You can change two terms but not one. You can change two terms but not one. A cis anti will give you a trio or a trans. Remember, this is a cis, it is anti-addition, so it will give you a trio. A trans in an anti-addition will give you an erythrio. Okay? And I have a table here that summarizes everything. This is a good summary of the stereochemistry. It summarizes everything. For addition of hydrogen, it will tell you that the addition of hydrogen is a syn addition. I know you guys cannot see it very well, but addition of hydrogen, it will tell you that it is always a syn addition, and that the cis will give you the erythrio isomer. Does that make sense? Then you can imagine what the trans will give you. Peroxyl acid, if you use the peroxyl acid, it's also a syn addition. If you use hydrobromination, it's a syn addition. And for all syn addition, the cis gives you the erythrio, the trans gives you the trio, TT. Okay? TT. Now, for syn addition, I will summarize it as STT. Okay? STT. It means that it is a syn, a trans gives me trio. Syn, trans gives trio. If it is syn addition, then you'll be able to know the other one, right? If you know one, then you can know the other. That's just what you need. Okay? And then it also gives you information about the anti. So those who are SRTs, so it's easy to remember this. Replace the R with T, so it becomes STTs, right? So I will recruit you as the STT of this class, no longer SRT. And so, yes.
You said that for that, before we wrote that sin, if you start with Z, you go to erythro.
Say that again.
If you start with, for sin, if you start with Z, which is cis, right? You go to erythro, right?
Yeah.
And then for anti, I had that if you start with E, you go to trio.
Yeah, but that's what we're saying, right? That's what STT is.
Yeah.
For a syn addition.
No, for anti, I had that with E, you go to trio.
For anti-addition, if you start with a trans, you'll be erythro. For anti-addition, if you start with a trans, your product will be erythro. Does that make sense? This is it here. Anti-addition, if you start with a trans, then your product will be erythro. Is that okay, guys? This one will be for those who will go and do biochemistry. That's why I say N. So let's go back to our last table. Remember this table? That's our summary table. That's our summary table. So we've been able to say which one is Markovnikov and which one is anti-Markovnikov. Okay? Now, we can now be able to decide. HBr will give me a racemate. It will produce a racemate. Okay? Mixture of R and S. Okay? And you are adding HBr, that gives me a racemate. So water and sulfuric acid will also give me a racemate. Hydroboration, we just talked about hydroboration. Is that a syn or an anti-addition? Hydroboration. Hydroboration is a syn addition. Okay. This one will produce a racemate. Ozonolysis, we don't know what ozonolysis will give us. Yes. Markovnikov, the R means a racemate. Bromination is Markovnikov. And the peroxo acid, this is peroxo acid, it's a syn addition, meaning that you are adding on the same side, peroxo acid. With the hydrogenation, hydrogenation is an example of a syn addition, meaning you are adding on the same side. Okay? Hydroboration, hydroboration is an example of an anti. Dibromination, dibromination is an example of an anti. Addition. Does that make sense? Are we good, guys? What can we do in 5 minutes? Huh? I will upload the video. I upload the video every day. All the time. What can we do in 5 minutes? No, you guys cannot go. I gave you guys 20 minutes at the beginning of the class, doing nothing. So next class will start chapter 9 on Tuesday and then finish it on Thursday. Well, we'll start it on Tuesday with the hope of finishing on Thursday or next Tuesday so that we can have time to review for the exam. Was that, yes? Say that again? No, it's done. Then please, I will emphasize. The only way you can get this thing done is by doing the work. I am doing my best. I'm telling you the truth. I cannot do better than what I'm doing now. Yes, I cannot do better than what I'm doing now. Make use of your textbook. You all have a textbook. You pay for the textbook. If you have a Mastering Chemistry account, it means that you have a textbook. Everybody with a Mastering Chemistry has an e-copy of the textbook. Go to your textbook and read. You guys can read English. And the textbook will explain things even better than what I do. English is not my language. But the textbook writes in good English. So go there and read. And then solve the problems. Solve them. My exam will be from your textbook. I will only get my questions from there. I'm repeating again. Please record this. I will take my exam question from the textbook. I have recorded it here. And the day your parent will come to my office and cry, I will pull out this video and play it in front of your parents, telling them that I will take my exam question from the textbook. The father of X or mother of Y. If your child failed my class, it's because he didn't solve problem from the textbook. This was recorded on February 13, 2020 at 9:13. Yes.